Hi class, let's take a look at example 2. Now example 2 is going to be a little bit more complex because it technically has a total of 3 coordinate points. And let me go back to the formulas. So if you're using a total of 2, then the appropriate formulas are actually here. But when you have more coordinate points, then it becomes a little bit messy. And then you're looking at, well, basically this equation here. So you're still going to have mx plus b, or in this case, it's expressed as b1x and actually b1x for the slope, and then b of 0. But because of the multiple coordinate points or more than 2, we're going to call that our regression equation. And then this is the scenario that you're going to be looking on more than 2 coordinate points, and that means that we may have a small interval where data was collected and we're looking at paired data x's and y's, and then we're trying to make a prediction. Are these coordinate points increasing, decreasing? Is there a pattern, and so on? So let's take a look at the first problem. And the first problem, what they ask us to do is to provide a scatter plot. Now, a scatter plot is just going to be a sketch with x's and y's, and some of these may be really messy. So you just need technically an estimation of values. So these are your x's, these are your y's. I'm just going to call this data set. And then the first coordinate point that we're going to plot is 1, 2. This is 1, 1, 2. That would be this coordinate point. 3, 4, 1, 2, 3, 4. And then actually it's 3, 4. So 1, 2, 3, 4. So it'll be 3 and technically 4 and 2, 2. So 1, 2. This will be 2, and that would be this coordinate point. And that's all it's needed. Let me double check. 1, 2. So this is 1, 1, 2, 3, 4. This is 3. It's technically at 4, and then 2, 2. So that would be our scatter plot. Nothing else to do here. Now, what we're evaluating in this portion for B is the equivalent or the closest value to the slope, and this is what we're going to get in terms of the correlation coefficient. Now, let me explain. It's a measure on how close our values happen to be within a linear pattern. So we're looking at a very small interval, and the idea here is that, well, this is the formula that we're going to be evaluating for each of the coordinate points. And this is really messy. It's technically x minus the mean over the standard deviation of the x's, y minus y bar, or the mean of the y's over the standard deviation divided by n minus 2. N is the total number of coordinate points. Now, we're using technology. So all you have to do is rewrite the formula. So in this case, let me just rewrite it. So our values of r, it's going to be the actual sum x minus x bar over sx times y minus y bar over sy divided by n minus 1, and n is equal to the values of 3, and we're looking at 3 coordinate points. Okay, now let me tell you the shortcut that evaluates this messy formula. And I need you to pull out your calculator. In this case, you're gonna enter the data set in the following form. So you're going to input your x's as L1 and your y's as L2. They do have to follow that format since the code already takes into account that the first data set is representing of the x's. So just go to the stats and then enter the data set. I already did this in advance, but let me double check. 132 first column, 242, and then exit. And let me give you the command that is going to actually evaluate most of what we're going to be doing in this short section. So you're going to hit stats, then move to test, and then all the way to the bottom. And this is just one way to evaluate. This would be, we're looking for the E linear regression t-test. And then all you have to do is hit enter. You just have to make sure that you have all your X's as L1, all your Y's as L2, and then do not modify anything in there, and then hit enter. Now, that code, that output technically has most of what we're going to be needing in this section. In this case, your value of R is all the way to the bottom, and we're looking at approximately 0.866. So this code is actually giving us that this is approximately 0.866. And let me just write it as we use the linear regression t-test to obtain the code. We didn't do this manually. If we had done it manually, we would have to create a table and then basically evaluate each X minus its mean divided by the standard deviation. Then once you get this value, you multiply times each Y minus the mean of the Y's and the standard deviation of the Y's. Once you multiplied every single one of those values, you divide by n minus 1. In this case, this is our actual answer. The value of R, it's 0.866. And what this represents, it's a measurement on how close your values happen to be to a linear pattern. Now, since we have coordinate points in space, and we're looking at small intervals, we're looking at small places where your data sets that were collected are close by. And any value near 1, it's going to represent a line going in this direction, -1 going in this direction. Near 0, there's really no pattern. And then from there, well, anywhere in between, you could also end up with a pattern that is not a line. Okay, so let's go back to where we were at. And in this case, our value was 0.866. Now, let's jump into C. In C, they're asking us to test for correlation. Now, what we're testing here is how good is this pattern that we're obtaining, assuming that the data is bell-shaped. And to test for correlation, you're going to need the following table. And that is this table. Let me show you how to read it. Your n represents the number of coordinate points. We have a total of 3 coordinate points. Our critical values are going to be 0.997. And then we're going to be looking at this chart. So in this case, let me provide the sketch. So we typically just put a line, a horizontal line. This is the values of 0, meaning that there's no linear pattern. The maximum that the formula is going to be for R is 1. The minimum is -1. Our critical values, so CVs, were plus or minus 0.997. So that means that we're going to have a critical value here, 0.997, and then another one here, -0.997. Now, the value of R that we calculated was R approximately 0.866. And then you're looking at the following chart. So you're looking at this sketch based on the chart. If it falls under in between the critical values, we typically say there appears to be no correlation because R is between the critical values. If it falls above it, we typically say there appears to be a positive correlation because R is greater than the critical value, or you could also end up with a negative correlation. So no correlation means that if we were to look at the data set, there is no evidence that there's a linear pattern. If you have positive correlation, your line is in this direction. Negative correlation is in between. And well, any value in between, you could get one of these two sketches. So in this case, we would say that there appears to be no correlation because R is in between the critical values. So let me rewrite it. Since R, it's approximately 0.866, is in between the CVs of plus or minus 0.997. Now, all of our statements are in terms of there appears or a statement that is likely. This is because the a new coordinate point could change everything in terms of, well, at the moment, we don't have evidence that we have a linear pattern, but adding a couple more coordinate points, you could end up with a positive slope line or a negative one. So that's actually it for this test. Now, let's actually find the regression equation. And to find the regression equation, technically everything was calculated. Because we're using more than 2 coordinate points, we're going to label it as a y hat. And we're just going to say that y hat is equal to the values of mx plus b. Now, what you're going to be actually looking into is this portion here, your output. So you're looking at y is equal to a plus bx. So the values of a are going to be 0.667. B is equal to 1. Now, B here represents your slope. So that would be bx. So I'm just going to say that y hat, it's approximately 1x plus, and I